Hello everyone. So for this week's tutorial, we will start to introduce how we can use data to fit an empirical model and use this model to further understand the process. Especially we will relate both the physical laws and the data together to see how they meet each other and give us insights into the process. Okay, so let's look at this question 8. It's the only question for this week. So if we got the following experimental data obtained from this cylindrical well-stirred water heater. So we have used this kind of the water heater as a tank system before. And if we have a step change in power supplied to this heater, we then get response data of the temperature like this. So the question asks us to find the system time constant using two methods and then compare to see if they agree with each other. And then based on this time constant, the next task is to find the overall heat transfer coefficient U and the heat change in heat input Q. So those are the constants we used in our previous mass energy and mass balance before. So it's given here that the ambient temperature is 70 degrees F. So we know the surrounding ambient temperature is a constant, and we know that through time temperature having this trend. So how's the system like if we just given the data? We first want to draw a process like this and see if this describes the data. So here I just use example we have studied, use a heater, use inflow. I give you this figure, but you should think again to see if it's really like this. Do we have this heater? Do we have this stir? Do we have the inflow, outflow based on the problem statement? And I also want to plot my data because I'm giving the time, giving the temperature, so I'm able to plot the whole data. Noting that initial starting point is a steady state. The time T at time 0 is the same as the ambient temperature, 70 degrees F. So this is very important because in all the transfer function, when we start to turn the time domain to Laplace domain, we use the deviation variable, which for temperature, for example, we will then use the real temperature minus the initial temperature. So your new variable will be this T minus 70. And out here in the previous example, use theta to describe the time. But actually here we don't suggest you to use theta because in the model fitting again, we use theta to indicate what the time delay, right? In the first order plus time delay model, we use theta to indicate time delay. But before we also use the theta for the temperature. So if we have theta I, that's us ambient temperature, also the inline temperature, and we have the theta as the outline temperature. Also, we have the temperature change with time. So looking at this diagram, it seems like a first order model can fit into this. So we can try. It doesn't hurt to try because when we fit some data model, it's always a trial and error process as well. We can try from first order. And here we see clearly starting to have this temperature increase trend. It seems no time delay in this case. So we can assume just a pure first order model. In the later stage, when we see results, if it's good, then we are happy about the first order model. If not good, we can further try other higher order model as well. But let's start to look at this. When we fit the model, we can directly based on the data curve to fit, but we want to get more understanding of the process first. Since we, so far in the class, we have all reviewed how we can build up the model from mass and energy balance. And for this process, we can actually derive its energy balance. So if you recall how we use this in the first week lecture or tutorial, we have shown you for this heater, if it's no inflow and outflow, we can get very simple and nice mass balance. So this is from the tutorial before. If we have a temperature change, rho VCP delta theta over delta T. So this is generally the accumulation of energy. This MCP delta T, delta temperature. And here is in the heating capacity of Q from the heater, minus the heat loss, the convection or the heat exchange with the ambient environment. So it's a UA as a heat transfer coefficient multiplied by this time difference, theta minus theta I. So in this case, we assume it's just a tank without inflow and outflow. Based on this, we then be able to derive all the terms, write group all the coefficients together and get this. Now we know it's like a first order description of the system, and we have the system tau and the defined constant. But when we look back to this problem and think about this in the Laplace domain, we can further transfer this time-dependent function to the S variable, to S domain function. So first step is always to define the deviation variable. So if we define the new theta prime equals theta minus theta 0, because we know here the theta 0 initial condition is 70 degrees. So we're able to define this new theta prime parameter and further derive this equation. So this gives us how we can get to from time domain function to the S domain function here. So this is the same, we derive the time domain and then got this theta prime term. Because here we initially have theta minus theta I, so this naturally becomes theta prime. And then the overall function can be written by grouping the coefficients together. The transfer function we can write as k over tau s plus 1. This is the energy balance for this tank reactor without flow. So because in this problem statement, they didn't say anything about if we have an inflow or outflow. So we can actually use this format, right? If you read again, we got experimental data from this well-stirred water heater. So we can stick to this format to see if the experimental data meet these physical laws that give us the value of the parameters. But if I want to add this flow, it's also possible because it still gives us a first order model. If you recall what we discussed before, if we have additional term accounting the inflow minus the outflow energy, then the whole process will give us this additional term of this flowing in light to the final time domain to this first order process again. The only difference is that we have tau and the constant defined in different format. We have additional term of QUCP here. Okay? So Q is volume flow in and flow out. If we turn this to the Laplace domain, similarly, we can get the theta prime, and also we will get the final constant to be different. So it's possible we can also use this format, but because we just focus on how we use the data to evaluate the parameters, let's stick to the first type of the heater. Let's assume it's low flow and see if our data fit into this model well. Okay, so recall we have the transfer function k over tau s plus 1. So for this first order model, without the time constant, right? With time constant is another term of e to the exponential of minus theta s. So here we just have this simple linear model, first order model. And then we reviewed in class for the general first order model, we are able to obtain, even with time delay we showed here, but first order similar techniques we discussed in the lecture notes. We are able to first use the slope intercept method, which means that we always plot this reaction response curve to plot this and read the initial slope and the interception to evaluate these parameters of k, theta, and tau in the model. So in the first order plus time delay, just a gain as k, time constant as tau, and we have a delay term as theta. But if just first order is good, we don't have this theta term. So if we recall in this more complex FOPTD model, we have certain curve like this kind of shape. So we can always get the initial value from we can get the k value, from the km from the final state first. So for this first order process, it's always reaching the final value of km starting from 0, because we define the deviation variable already. So it's starting from 0 until km, and then the first initial slope will give us the 1 over tau value, because if we calculate the 1 over y over km, gets the function, and takes the first order derivative over t at the time 0, we get the slope has a value of 1 over tau. So in the lecture we discuss more. If we want to further evaluate this time delay theta, we can then get this inflection point when the trend becomes different. We got this tangent line here and evaluate this time delay theta. Because this curve initially we saw is no time delay here, so we can just simplify it to a first order term. So this is how we define the slope intercept method. We can also use the graphic techniques, which is a lot empirical laws based on past data, past experience. We estimate that. So here it says that the response gets 63.2% of its final response time at t equals tau plus theta. So this is magic number, 63.2%. So we just got this time, the total value is tau plus theta. But if for first order we don't have delay, theta is 0, so the total at this magic percentage will just be the time constant tau. So this is the law we can also use. It can be another simple method from the graphic. Okay, so this is something we learned in the lecture. Then let's apply these rules to the example we have here. So again, we got the plot from the experimental data. And first, if we want to fit the first order model, we know this is a step input with a step response. We can plot it. And the initial slope is written here for y over km at initial state. This initial slope is 1 over tau. But based on this discrete data point, we can either get this figure and then draw the slope, draw the tangent line to read the slope. But more simplified method, we can directly go back to look at the data, because we know initially it is 70 degree F, and after 4 minutes it becomes 80. So this is the initial time. We just use these 2 points to do the estimation of the initial slope. That's just because all the methods are based on estimation, approximated description of the model. So we can use these initial 2 points to estimate its slope. So this initial slope is evaluated to be 1 over tau, because we know the temperature difference is 10 divided by the time difference 4 minutes. And this value will be equal to k, 1 over tau. And we need to divide again this value by km. Okay, so km, what is the km here? We read from our figure already. Because we have the deviation y, so we got the km to be the 170 minus the 70 at the initial state. So that's the final value of km, that is 100. Okay, so I know my final km is here. I know my 1 over tau has a value of 10 over 4. And then use this function, we're able to calculate my time constant tau is 40 seconds. Okay. So this is based on the slope intercept method. And then if we just want to use an estimation method, as we said, the magic number 0.632, we know at this point when the final change is this. So because this is deviation variable, and if we turn this to the final exact temperature, we know this is 63.2% of the total response difference is 100 multiplied by 100 and plus 70 initial value. So this is a real temperature to read from the figure. At 133.2, we draw a straight line and read the corresponding time. Based on this same figure, we know that this time will be the time constant for this model. Okay. So we read that to be nearly 40 minutes. So that gives us the agreement between these two methods. Of course, if you do the detailed calculation or something, there may be some mismatch. We cannot, because all the data-driven model has certain errors, but these errors are within the acceptable range. So we say these two methods agree with each other. Okay? So this is method 2. And next step, we want to find the overall heat transfer coefficient and the change in heat input. Since we know the value of T and tau from the transfer function, the next task, if we want to relate the transfer function back to the real process, the step is just to link this to the original physical model. Because we know we can assume this tank is just a setting joule, so we have the total area and the volume that can be calculated based on the matrix given. And then using this tau and the K formulation, we are able to know what is the exact coefficient. This is the overall idea. So here's the area, because it's like a tank, so we only have the surrounding area and the bottom area for heat transfer. It's open surface at the top with a stir. So the total area of the cylinder wall plus the bottom will that just be 2 pi r of the diameter multiplied by h to be the total area for the cylinder wall plus pi r squared to be the bottom area. That's the value for A. And similarly, the volume is pi r squared multiplied by h. We got the V term here. And recall that from the physical model, tau equals UVCP divided by UA. So initially when we derive the model, we don't know this tau is a time constant, but when we transfer to time to Laplace domain to the S domain, this becomes a time constant in the first order model. So we are able to estimate this tau from our data and then link this tau back to the U formulation, because we know rho and Cp are just physical parameters, and volume is calculated, area is calculated, tau is given from before. So the whole value, just do the unit consistency check, we're able to get the final value for U. Okay, this is how we get the heat transfer coefficient. And similarly, we want to get the change in heat input Q. So here, how do we get this? Because we know the response of the system from this curve, from the given data, we know the final response gives certain temperature change. Therefore, we want to use this temperature change to refer back to the initial heat change. So this can be regarded as some corresponding delta Y to this input change, delta U, as we are familiar with. That is what the transfer function means. Transfer function, if we got a transfer function constant, it exactly means the ratio of input change to the output change at steady state. Right? So if we recall here, we are able to get a value of K. And then this K will just be defined as delta Y over delta U. So this is from what transfer function means. This is from what this K means for any system. So for any system, this constant gain just means a change in the output related to a delta change in input. Therefore, we can use this K to write again. We know our output change here is a certain temperature, is 100 degree F. And then based on the output, what is my input change. So we can directly use this format to get the delta U. Because we know K is also defined from the physical laws by 1 over UA. This is from originally. Since we already calculated the U value for this process, so we multiplied it by A, we can get this UA as a heat transfer coefficient multiplied by area, and then multiply by this temperature change of 100 to get the corresponding inlet change in Q. So this is the overall idea. Again, the key thing is about using the physical meaning of these process parameters to link them to the data, to get the value estimated from data and then link back to physical meaning, and then again using the physical meaning to explain what is a change, input change, output change relationship. So this is the part we got the change in heat temperature in the heat input Q. And again, they're not limited to one single method for this. If they give you a data, you can use a regression, you can use this curve to read, and we also show you some additional methods in the book. You can use this for all the methods to fit the first order plus time delay model. If you want to fit a first order without time delay, just theta equals 0. So it's similar methods. It can also be applied. You can also use the neural network model we introduced. It's just to fit the data using neural networks to fit a regression model. It's also a data-driven model to describe the process. So all those things can be used based on how your data is like, based on what data you can get from experiments, and then obtain a model from the data, and then use the model obtained to further explain the inherent physical laws and the chemical reactions linking to the process itself. To understand the model, it's like the way you explain the data-driven model, linking back to the process itself, using it, making it no longer a black box model. So this is the core idea of this tutorial. Okay, thank you.